Determine the domain of the following logarithmic functions algebraically. Recall that the argument of a logarithmic function must be strictly positive. So that's how we find the domain of the logarithmic function, is we take the argument, which in this case is 2x plus 1, we set it greater than 0, and figure out who are the x's that make that happen. To solve for x, we subtract 1 from both sides. We get 2x is greater than negative 1, and then divide by 2 to get x is greater than negative 1/2. So we'll formalize our answer and write it in interval notation. The domain of this logarithmic function is going to be from negative 1/2 to positive infinity, and we do not include the negative 1/2. So here in part B, again, we are going to take the argument of the logarithmic function, set it greater than 0, and then solve for x. The argument in this case is x squared. So we need to figure out who are the x's that make this value positive. Setting the argument greater than 0 brings us to a quadratic inequality. And there are two main ways that we can proceed to solve this quadratic inequality. One is the boundary point method, and the other is the graphing method. I think this one is far easier to solve with the graphing method, but let's separate our quadratic inequality from the original function to overemphasize that what we're going to be graphing is the quadratic equation, not the logarithmic equation from the beginning. We basically want to let y equal to x squared and then graph this parabola that opens up to then determine where the y values are greater than 0. Y is equal to x squared is a parabola that opens up, and the y values on this graph are greater than 0 in this region and in this region, but y is equal to 0 at this point, which is not actually allowed. We need those y values to be strictly greater than 0, not equal to 0. So the x values that solve this inequality start at negative infinity and go to 0. We leave 0 out because when x is equal to 0, the y is equal to 0, that's not allowed. So we pick right back up at 0 and we go off to positive infinity. So the x values that solve this inequality are the same x values that will keep the argument of this logarithm positive. And so those x values are what make up the domain of this logarithmic function. So the domain is from negative infinity to 0, and then from 0 to positive infinity. We'll look at one more example here. Again, we want to figure out who are the x values that will ensure that the argument of the logarithm is a positive quantity. So we will extract that argument, create an inequality, and then solve for x. The inequality that we have now is a rational inequality. And again, this rational inequality can be solved in one of two ways, with the boundary point method or the graph method. So let's delineate this subproblem from the original problem so that we can focus on it. So this time, let's use the boundary point method to solve the rational inequality. And the boundary points are going to be obtained from looking at the zeros of the numerator and the zeros of the denominator. We then take these two boundary points, plot them on the number line, and test values inside each of the resulting intervals. So let's test x is equal to negative 1 back into the inequality to see if the values in that interval make the argument positive. When plugging negative 1 in for x, we get negative 1 on the top over negative 2 in the bottom, which is positive 1/2, and therefore this interval works. Now let's test x is equal to positive 1/2 for any value in between 0 and 1. So here we have positive 1/2 over 1/2 minus 1, which is negative 1/2. This ratio is negative 1, which is not greater than 0, so this interval is not going to work. Now let's choose a test value that is in the greater than 1 interval. Let's say x is equal to 2. When we plug 2 back into the original inequality, we get 2 over 1, which is a positive quantity, so that interval will also work. We also need to think about the boundary points themselves. When x is equal to 0, we get 0 over negative 1. That's equal to 0, but equal to 0 is not allowed, so this boundary point does not work. We also need to test x is equal to 1, and when x is 1, we get 1 over 0, which is undefined, and therefore this boundary point doesn't work either. So now let's put all this together to say that the solution to this rational inequality is going to be the x values that start from negative infinity and they go all the way up to x is equal to 0, which is the boundary point. We are going to leave out 0, and that is this interval that we've declared as a working interval. This interval doesn't work, nor do the boundary points, and so we're going to skip over that region and then say the next working interval starts at x is equal to 1, the boundary point, not including it, and then it goes all the way out to positive infinity. So these are the x values that solve this rational inequality, and therefore they are the x values that cause the argument to be positive. So those are also the x values that make up the domain of this logarithmic function.